Hey guys, today we are going to be discussing a video I came across by Flat Earth femtard Orphan Red. In this video, Orphan Red describes in detail her misunderstanding of quantum mechanics, more specifically, the observer effect. While I originally wanted this video to be about 15 to 20 minutes long, after typing out the script and doing the math, I realized that this is going to be a long one. So sit back, grab your calculators, and let's begin.
The fact that these things must be observed is significant.
Not a good start, Orphan. What things are we discussing and why are they significant?
Because we're told by science, by physics, that if a particle is unobserved, then it exists in a probability distribution wave state, a superposition state of all possible properties.
Oh boy, this is going to be interesting. Are you really about to try to explain superposition in quantum mechanics? I may just need a new idiot meter after this video.
And this probability distribution is actually distributed across the entire universe.
You're an idiot.
Yes, but the probability distribution is typically applied to only atomic and subatomic particles. We will get more into detail when discussing Heisenberg's uncertainty principle and de Broglie's wavelength later in this video.
And so it's only when a particle is detected by a conscious observer.
You're an idiot.
Detected, Orphan Red, not observed. These words have significant differences in meanings when discussing quantum physics.
That it takes on fixed properties.
You're an idiot.
And now we get to the root of your ignorance. The observer effect is probably the most misunderstood phenomenon in quantum physics. The idea is that a conscious observer can bring a physical object into existence with the simple act of observation. Just ask Deepak Chopra. This is patently untrue though. In this case, the act of conscious observation causes the probability distribution wave to collapse into a singular particle that takes on the defined properties of the wave. This misunderstanding is in the term observation. Many people believe observation occurs from inside the body moving outwards, as if the act of observation had something to do with the ability to observe the particle, when in fact, it is the methodology used to observe something that causes the collapse of the probability wave. Ask yourself this: what does it take for something to be observed? For humans to observe something with their eyes, a ray of light must reflect off of that something and be directed into the lens of the human eye. Therefore, for a particle to be observed or detected, an outside system must interact with the probability wave, causing the wave to collapse or quantize into a particular location along the distribution wave. There are many different interpretations on how this actually happens, and I'll be linking to videos in the description that will help you understand the different ideas on how this occurs.
And in that moment, then it is localizable.
I'm actually quite surprised that you use the word localizable correctly. Localization is the process by which the probability wave of a particle collapses into a single, localized, and measurable particle. There are conflicting ideas among physicists today as to why and how this happens. Some believe the wave collapses to a particle, some believe it is a wave of particles with identical properties that choose one based on probability when measured, and yet another group believes the particle was a particle the whole time, traveling along the wave function to its final destination. The problem is that they all start in the same position and they all end in the same position, and the mechanics by which they travel between the two locations can never be observed. Weird, I know, but it's testably and repeatably true.
So prior to being observed,
Detected, Orphan Red.
the particle has a probability of being located if you look in any space in the given universe.
You're an idiot.
What? This is completely nonsensical. I think she is trying to apply Heisenberg's uncertainty principle to explain the possibility of a particle being in any space at any time. Again, we are going to be covering that in more detail momentarily.
And so your probability of finding the particle, if you look here, might be 0.001%. And if you look over here, the probability might be 0.02%. Over here, it might be 3%.
Okay, so I guess we will begin discussing the Heisenberg uncertainty principle now. First, the Heisenberg uncertainty principle has the most practical applications when discussing atomic and subatomic particles. It states that the uncertainty in the location of a particle times the uncertainty of the momentum of the particle must be greater than or equal to Planck's constant divided by 4 pi. Basically, this equation describes an inverse relationship between the uncertainty of momentum versus the uncertainty of location. In other words, as the uncertainty of the location increases, the uncertainty of the momentum decreases, and vice versa. I'm not going to ruin the rest of the video by going into too much detail about Heisenberg's uncertainty principle just yet, but I will be covering it in detail when refuting her arguments.
But over the entire universe, that's where the probability of finding the particle, if you look in any given point, really, that's the spread of the probability distribution wave.
Not necessarily, Orphan. While there is a minute probability for a subatomic particle to be located anywhere in the universe prior to being measured, the actual position when measured will ultimately be somewhere close to where it is predicted to be. So while there is a probability that an unmeasured electron on a hydrogen atom near Proxima Centauri is actually located here on Earth, the possibility is so small that it should be considered improbable to the point that it is impossible. In fact, this is exactly what the Heisenberg uncertainty equation more accurately predicts.
And so it's only for observed things that the concept of space even makes any kind of sense.
Wow! You're an idiot!
So this is an example of the philosophical ideology that quantum physics has opened. The distance measured between two objects only matters when observing the two objects. This is similar to the riddle of if a tree falls in the forest and nobody is there to hear it, will it actually make a sound? Basically, it describes a concept that dives into the idea that if no conscious observer is observing a star, does the star actually exist? Which is impossible to prove because you have to make an observation to see if the star is there or not. And every time you look, it's there. But how do you know that the star is still there when you are not observing it? De Broglie's wavelength covers why this is not actually applicable to anything larger than an atomic or subatomic particle, and we will cover that later in this video.
Because space is a relative concept that we apply to distinguish the distance between things in a way that's meaningful to us as conscious creatures.
And you are an idiot. When you say space, do you mean outer space, the space between two objects in outer space, or the unoccupied space between your ears? Your word salad tastes like space bullshit. I think what you are trying to say is that we apply units of measurements like meters and light years to describe the distance between objects that exist in space.
But that space isn't real. That distance between objects, it's not actually real, because prior to our observation, it doesn't exist.
If the distance between objects isn't real, then how come a distance even exists between any two objects in the universe? You are grossly misrepresenting the concept of the duality of particles, and I don't think you completely understand what it means to make an observation. So I can't figure out why you are even bringing up the observer effect in the first place. Orphan Red, you are an idiot.
The probability distribution wave of both objects overlap.
Yeah, but while the probability wave overlaps for both objects, it is impossible for both objects to occupy the same point in space at the same time. So the probability distribution wave should be used for prediction purposes only. Once an interaction with an outside system occurs and information on the particle's location or momentum can be detected, the probability wave collapses and becomes non-existent.
And so there is no distance between them. There's no space between any unobserved objects.
Saying there is no space over and over is very flat earther of you. However, like the rest of your flat earth arguments, just saying it repeatedly doesn't make it true. You are an idiot.
Because every particle in our universe has a probability distribution wave covering the entirety of the universe. And so
you are an idiot. Did you stop at the probability distribution wave and not research any other concepts of quantum physics? De Broglie's wavelength and the Heisenberg uncertainty principle both help describe which particles are affected by the probability distribution wave in practicality and the amount of uncertainty associated with each of these particles.
Each object's probability distribution wave will overlap with the probability distribution wave of every other unobserved particle in the entire universe.
And you are an idiot. Again, while there is a calculable probability for any two particles to occupy the same point in space at the same point in time, reality tells us that this is impossible. This is one of the main reasons why the probability distribution wave is only applicable when the particle is undetected. Any and all means of detecting the position or velocity of the particle will cause the distribution wave to collapse into a single point based on the wave function of the probability wave.
And so there is no space between unobserved objects. There's no space.
And you are a fucking idiot.
There is no reality that corresponds to that concept, to that label that human beings apply to an observation that only conscious creatures make, but that isn't actually necessarily real.
Orphan read, did you just confuse yourself? Because you confused the shit out of me. What you said makes absolutely no sense whatsoever. After breaking down what you said into normal people's sentences, it states that there is no reality that corresponds to the human being idea of measurements to observations made by human beings that aren't actually real. Yeah, and you are a fucking idiot.
And we know from physics.
Oh really? You know from physics. This should be golden.
That particles that manifest and take on fixed properties and a set location, they do slip back into superposition states. And so if you observe a thing and then you leave it, after some time, it will go back into a superposition state.
Okay, so this was the one part of the video I had to do a little in-depth research for. As I was taught, when the quantum wave function collapses, the particle will remain localized. What Orphan read is saying is that once the particle is unobserved, it will delocalize and return into a superposition state. The reason I disagree with this assumption is that you would have to define when the particle goes back into superposition state. In other words, in the double slit experiment, if the test added another pair of slits between the first pair of slits and the collector plate, then the collector plate would get a probability wave even after the particle has localized. So for this to be reality, you would have to define when the particle actually goes back into a superposition state. As it stands, the collector plate records individual localized particles that are not in superposition. Therefore, you would have to define a set of requirements for the particle to consistently go back into a superposition at a certain time. Before I refute this position with an example, I will give you an example to support Orphan's position. And for this example, I will be referring to Schrodinger's cat. If you're not familiar with Schrodinger's cat, you should do some research, as it unintentionally became the framework of quantum theory. Before being observed, Schrodinger's cat is both alive and dead, and the localized properties of alive or dead aren't set until an observer opens the box and measures the state of the cat as being either alive or dead. So in this example, we are going to say that the cat has been observed and is alive. However, the cat has now jumped out of the radioactive box and walked out the door around a corner so that we can no longer see it. According to Orphan, at this point, the cat has essentially slipped back into a superposition state, as it can be anywhere around that corner, including anywhere in the universe. For you to determine the cat's position, you would first need to build a probability wave based on the cat's properties and attributes. If you properly calculated the probability wave function, then when you walk around the corner, the cat should be somewhere within your predicted position. And while according to quantum theory, the unobserved cat could possibly be located anywhere in the universe, we know that the cat is, in fact, somewhere around the corner. The longer we wait to check the cat's position, the larger the probability distribution wave will get, so that if the time between measurements is infinite, then the cat truly has the possibility of being anywhere in the universe. Now for my example, I'm going to use something with a little bit more common sense. A pitcher is standing on the mound and is getting ready to throw a baseball towards home plate. Now anybody who has ever watched baseball knows that while 99.99% of the pitches go in their intended direction of home plate, every so often the pitcher will make an errant throw and the ball will travel towards third or first base, or even slip completely out of the pitcher's hand altogether. For my example, we will only be focused on the pitches that reside in the highest probability, which are the pitches directed at home plate. Until the point that the pitch is thrown, all possibilities have the same probability. If there is no one to observe the pitch, the position of the ball over the plate cannot be determined until the catcher catches the ball. At that point, the location and the path taken by the ball are localized and determined. The point is, we don't know the path the ball took until it interacted with the catcher. Now let's add cameras every few feet. As the ball travels down its path from pitcher to catcher, the cameras are taking pictures of the ball's position. With each picture, the ball becomes localized or measured, and the future path of the baseball can be predicted with more certainty than if it was never measured. And with more and more pictures, we become more and more certain of its final travel path and final position. The fact that there is a time when the ball was traveling between cameras doesn't give the ball the ability to delocalize and be on the other side of the universe while being unobserved. I will give Orphan this one concession though. There is nothing in quantum theory that disallows the probability of the baseball being anywhere in the universe when unobserved. I keep referring to Heisenberg's uncertainty principle and de Broglie's wavelength, and I promise that we are getting there shortly as they merge the probability distribution wave with the relative location possibility in reality.
That's what we know about particles, and things are made up of particles. And so it's not enough to observe, let's say, another solar system. And if there's no conscious life in that solar system, then your observation of that solar system effectively brings it into manifestation, into reality.
And you are a fucking idiot, as this is completely incorrect, and a good time to introduce de Broglie's wavelength and why this is important when it comes to the practicality of superposition on small and large objects like electrons and stars. De Broglie's wavelength describes the impact of the superposition of any object on the realistic location of that object. De Broglie's wavelength reads as lambda equals Planck's constant divided by the momentum of that object. Since momentum is a product of mass times velocity, as the particle or object gets bigger and faster, de Broglie's wavelength gets smaller and smaller. For superposition to play a significant role in an object's location, the size of the object needs to be equal to or less than de Broglie's wavelength. Therefore, a singular electron around a hydrogen atom with a mass of 9.11 times 10 to the negative 31 kilograms and a speed of 2.2 times 10 to the meters per second has a de Broglie's wavelength of 3.306 times 10 to the negative 10 meters, or 330.63 picometers, while the radius of the hydrogen atom is only 53.92 picometers. Since de Broglie's wavelength is 6 times larger than the radius of the electron orbit at ground state, the uncertainty of the position of the electron is extremely high. In fact, there is a probability that you will find the electron further away from the atom than the ground state orbit predictably allows. We will come back to this example when calculating for the uncertainty of the position of the electron using Heisenberg's uncertainty principle, but first let's now calculate for the de Broglie's wavelength of our sun. The accepted scientific values for the mass and velocity of the sun are as follows. 1.989 times 10 to the 30 kilograms of mass, and according to the Stanford Solar Center, the sun is traveling through space at a velocity of 72,000 kilometers per hour or 20,000 meters per second. Using the formula for de Broglie's wavelength, we get the value of 1.666 times 10 to the negative 56 picometers. That's not even close to 1% of 1% of 1% of a Planck's length of distance, which is the smallest unit theoretically possible to measure. And when I say not even close, I mean I would have to say that another 15 times or so to start getting close to the percentage of a Planck's distance this value represents. It's basically so small that the superposition of our sun is not worth mentioning for practical and testable purposes.
It makes it real for all intents and purposes. It gives it tangible reality. Because when we check, we observe them. And as soon as you observe them, then they take on set properties.
So I didn't want to dive too much into this portion of quantum physics, but what Orphan Red is describing is the Copenhagen interpretation. To dumb it down, the Copenhagen interpretation relies on a measurement or interaction to take place for the distribution wave to collapse into a singular particle. Where the misconception lies, and it does so here with Orphan Red, is the assumption that the observation must be made by a conscious observer, when in reality, it is the ability to receive information about a particle that causes the probability wave to collapse. For example, in the double-slit experiment, when unobserved or measured, single electrons will travel through space along a wave function before collapsing at a location somewhere within the probability distribution wave. We know this because the wave interacts with the detector and a collapse occurs, allowing the electron to localize and become observed, detected, or measured. Basically, for any observation to take place, there must be some form of interaction with the probability wave, resulting in information about the particle's location or momentum leaking out to the observer, causing the collapse of the wave into a single particle.
And so at some point, that solar system that you had observed will slip back into a probability distribution wave of various properties and location information.
So I guess this is as good a time as ever to inject Heisenberg's uncertainty principle. The Heisenberg uncertainty principle describes an inverse relationship between the uncertainty of an object's position versus the uncertainty of the same object's momentum. It reads as the uncertainty of an object's position times the uncertainty of the momentum of the object is greater than or equal to Planck's constant divided by 4 pi. Basically, it represents how an increase in uncertainty of an object's location results in a decrease in the uncertainty of its momentum. And if the uncertainty of the momentum increases, then the uncertainty on the position of the particle decreases. This uncertainty of location is significant to smaller particles like atomic and subatomic particles, but for objects larger than atomic and subatomic sized particles, the uncertainty of location becomes insignificant and unmeasurable. We will use the same examples as before to calculate for the amount of uncertainty of location for the sun and an electron. The uncertainty of momentum is calculated by multiplying the mass of an object by its uncertainty of velocity, or delta V. We will keep the uncertainty of velocity the same at 1 meter per second for simplicity purposes. To find the uncertainty of location, delta x, we must first divide both sides of the equation by the uncertainty of momentum, or delta P. This leaves us with the equation of delta x equals Planck's constant divided by 4 pi times delta P. Let's solve first for delta P for the electron and then the sun. Delta P for the electron equals the mass times delta V, which we established as 1 meter per second, or 9.11 times 10 to the negative 31 kilograms. Delta P for the sun is the same equation with the mass of the sun being 1.989 times 10 to the 30 kilograms. Plugging both into their respective equations gives us delta x for each object. The electron has an uncertainty of location, or delta x, of 5.788 times 10 to the negative 5 meters, or 57.88 micrometers, while the sun has a delta x of 2.651 times 10 to the negative 65 meters, or not fucking measurable. Because delta P relies heavily on the mass of the object and delta X is inversely proportional to delta P, the larger the mass of the object, the less uncertainty in the position when the object is not directly interacting with another system.
And so the distance that you had measured between yourself and that solar system becomes wrong, becomes meaningless, because that solar system will then revert back to a probability distribution wave that is spread out throughout the universe.
So back to our previous example, if you took multiple measurements of the distance between yourself and the sun, and on the first measurement you get a value of exactly 1 light year away, during the time between measurements, the uncertainty in the sun's location, while unmeasured, would be 2.651 times 10 to the negative 65 meters, which is essentially 0 in our reality, and would be exactly 1 light year away when measured again. The electron, on the other hand, is extremely tiny, and while there is a debate on the exact radius of the electron, the scientific consensus is that it is smaller than 10 to the negative 15 meters or 10 to the negative 9 micrometers. The electron in the example given would have an uncertainty of location of at least 57,883 times larger than the size of the electron itself. This is why the Heisenberg uncertainty principle primarily applies to particles that are of atomic and subatomic sizes and is irrelevant to objects that have even a small but significant mass. Orphan read, I still don't understand why you stopped learning these principles at the observer effect. Maybe because you are a fucking idiot.
And so it effectively is everywhere. There's a probability of locating it at every single point in space.
And you are a fucking idiot. Just because you are not looking at the sun doesn't mean that it has a possibility of being here on Earth.
And so the distance measured is invalid because it no longer applies, because you could just as easily say, well, the distance between me and that solar system that is now in a superposition state that has reverted back to a probability distribution wave, what is the distance between me and it?
What the fuck does that even mean? As discussed, the distance measured is invalid by an insignificant amount. Plus, the solar system itself will never revert to a superposition state. The problem you are having is thinking that your personal observation is special and has caused the universe to manifest itself into existence. It is not your observation that causes the collapse of the wave function, but the interaction with any system that results in measurable information about the solar system that causes the collapse. Starlight from another star light years away would be sufficient to theoretically cause a solar system that is in a supposed state of superposition to collapse into existence, even without someone there to observe it. The observer effect has taken over the philosophical side of quantum physics. To research this theory more, Google Copenhagen interpretation of quantum physics, which is what Orphan Red should have done, but she is a fucking idiot. Don't be an Orphan Red.
Well, there's a point right in front of you that has a portion of that probability distribution wave.
What the fuck, Orphan? I'm starting to get the feeling that you don't even have the most basic understanding of quantum physics. Start with Schrodinger's equation. Actually, fuck that. Start with remedial math, because you are a fucking idiot.
And it may just be 0.000000000 ad absurdum 1%, but that's still a probability of finding the solar system in that location if you were to look there. There's no meaning to the concept of distance, of space.
Wow, there is no meaning to what the fuck you just said, Orphan Red. You are a fucking idiot.
I'm saying this is what follows from science today, as it's given to us, as it's published, as it's understood by scientists, physicists.
Actually, this statement is very true. Quantum physics is the most accurate and beautiful explanation of the reality that we live in. In short, quantum physics almost perfectly describes the realistic nature of 3 out of the 4 natural forces, leaving only gravity to be explained. This is where general relativity picks up. While quantum mechanics picks up the slack when conventional gravity falls apart at the microscopic level, general relativity takes command when quantum physics falls apart at the macroscopic level. In other words, things that are too small for us to physically interact with are governed by quantum mechanics, and things that are big enough for us to physically manipulate are governed by general relativity. One of the next steps in furthering the understanding of quantum physics will be the development of an equation that ties general relativity to quantum mechanics.
If you believe in science, then this is what you must believe, because this is what science says is true. This is how science explains the world. This is the theory of how things work. And if you believe in what science tells us, then this is part of that story that you buy into. If you buy into space-time, if you buy into particle physics.
If you are watching this, then you are actively using quantum mechanics. The modern day transistor does not work without quantum mechanics. Almost everything you use on a daily basis is developed with the understanding of quantum mechanics. Orphan read, "You are dumb as fuck, and you are a fucking idiot." She then goes on to give a pathetic example using a video game, which actually touches more on the subject of simulation theory, which I wouldn't mind doing a video about if you guys are interested. So if you'd like to see some content on simulation theory or anything else involving quantum mechanics, please leave a comment below. Quantum physics is hard to wrap your head around. It allows for some truly mind-bending events to occur that simply can't be explained by classical physics and general relativity. But it is not the end game. It is merely a stepping stone to the next great theory that will hopefully one day describe everything, unifying the big with the small. What truly bothers me about Orphan Red, and most flat earthers for that matter, is that she obviously had to do some research about quantum mechanics to make her video. She has apparently at least learned the basic concepts, but it was in an effort to disprove the functionality of quantum mechanics. Quantum mechanics works regardless of the shape of the Earth, and with just a tad bit more of in-depth research, you could have seen the results from the many tests that have been performed and are still being performed, and analyzed the data yourself. Orphan Red, your attempts to disprove modern science is undeniable proof that you are a fucking idiot.
And so, that's that. Good night.
Now, I'd like to take the time out to thank Orphan Funbags and her usage of quantum mechanics to try to disprove quantum mechanics. It is the equivalent of shooting yourself in the head to disprove that shooting yourself in the head is not lethal. Orphan Red, you are a fucking idiot. Quantum theory is one of the most interesting concepts of our reality, and in my opinion, the closest thing to science fiction in real life. If you are like me and constantly trying to improve your educated knowledge base, I highly recommend watching the many instructive courses on quantum physics across the internet. As a bonus, I will be adding a list of videos and a playlist for my viewers to watch if they want to further their understanding of quantum mechanics themselves. If you didn't like this video, please leave a comment below explaining why you are an idiot apologist, and me or one of my subscribers will address you. And if you enjoyed this video, don't forget to like, comment, subscribe, and click that little bell so that you won't miss out on future videos and live streams. I'm Father Skeptic, and I'm out.